And John, where'd John go? Thank you, John, for helping make this thing happen. Let me get out of the way of my own screen here. Hopefully everyone online is able to see the screen here.
The screen is shared, so you can stand in front of it. You're not blocking anybody online.
Okay. So I'm David Landry. I've been in this industry for 30 years. I love it. I can get very evangelical about the potentials of concrete, which have really it's in its infancy at this point. And here we are talking about low carbon concrete. But we can go back 2,000 years to the Pantheon in Rome, and the dome there is unreinforced concrete. We're not positive what the Romans used to heat and calcine their cement and pozzolan, but we're going to guess it wasn't geothermal, and they probably used fire. They probably had a CO2 footprint of about 0.1 tons per yard. So a tenth of basically 9 times better than we are today at making concrete, and that thing is still standing. So if we can't do better than the Romans, let's just go home now, because it's been done. And that's really a pretty much gold standard in many ways to this day as we think about this issue. One thing is I don't spend a lot of time going through the resources, because going through carbon calculators with everybody and things like that can be tedious. However, this is something that I would like to see, I would highly recommend everybody get this guide right here. This is, if you can find a consensus between the status quo, no offense to Heidelberg, and all the big ready-mix guys and the Portland Cement Association and the ACI, which are going to slow roll the carbon neutrality out as far as they can in all likelihood, and a very aggressive schedule to carbon neutrality. These guys did a pretty good job. Don Davies from our local MKA, former president there, led this task force. And as you go through here, I just point this out. Oh, is this working? Oh. As you go through here and you see how it classifies global warming potential and timelines, you're going to get to a point where you realize, okay, do I really want to go through all this? And the answer is if it's structural, then the codes of the ACI and the American Society of Civil Engineers will dictate, yes, you're going to go through this and you're going to use prescriptive mixed designs. But when we look at the world, the built environment, how many things are made of concrete that are non-structural? And just start throwing things out. Retaining walls, sidewalks, curb and gutters, catch basins. What else? Roads. Well, the bridges and freeways, but yeah, general residential. Right. You know, you get plenty of strength out of 2,500 psi concrete to build a ton of objects. We've got vertical gardens going. We've got all kinds of interesting projects that Lindsay's working on. And single story is certainly achievable with lower PSI mixes. But the reason I bring that up is because you have the carbon calculators in here that are being publicly sourced, and it's going to provide a database. And this is how you can move the ball forward towards carbon neutrality, is by participating in that calculator that they provide. So we'll just go back to presentation. How many of you have done a low carbon concrete project of any kind where you really pushed it? Anyone? 1, 2, 3, 4. You don't count. Ray?
I got a low carbon project I'm working on right now.
Good. So here in Seattle, we a lot of people have heard of Portland limestone and all that. It's been around for a long time, but it was used at such low levels, like 7%. Nobody even knew the limestone replacement had gone in there. If we were to reinvent concrete, Portland cement wouldn't be the binder of choice. And just for the basics, there's 4 basic ingredients you have to have in concrete: cement, sand, aggregate, and water. Okay? You get a lot of accelerants and admixtures and rheology additives and plasticizers, all sorts of things that pile onto that list. But that's still the basic 4 elements. Okay? And the nasty little secret, which is no secret anymore, is the binder, Portland cement, creates a lot of CO2 when it's being calcined, turned into clinker, not to mention the actual heating mechanism. So that's where the idea of lowering, concrete's very indispensable. People wanted to lower it, and there were a lot of different avenues to doing that. Lowering the CO2 of the cement's a big start. Supplemental cement materials, fly ash, slags, other natural minerals are able to substitute out the amount of Portland cement you need. So that's a big category. Carbon capture, I could wow you, would dazzle you with pictures of CCS out of Norway and Brevik company, and their sequestering of CO2 and sinking it into concrete and sinking it into the ocean. Exciting, except I want to give you guys actionable things you can take now into market that are available here. Next thing is lower CO2 aggregates. Aggregates produced actually with CO2. Blue Planet is one of the companies doing that, as well as some others. Volumetric offsets using recycled content and waste streams. This would be materials that basically are inert and they go right into the concrete. Like this is end of life. You can't upcycle this plastic anymore. It gets to a point there's nothing you can do with it. So put 10% in the concrete. You don't decrease the concrete, but you increase your volume by 10%. So again, it's contributing to lowering the amount of volume of cement. And then finally, I would say, it's important. Don't get static. Don't get static in your creativity here. Concrete is an inert material that can do a lot of things, and there could be materials that have not yet even been invented or tested. I'm blown away by. I've spent 30 years in this industry and looking around at all the new materials I can, mostly for concrete repair materials. Real interest in polymers and rheology agents. Specifically, I had on my product development board a couple of dentists who were biochemists, and dentistry was using the most sophisticated ceramic cements that were biophilic, that work with your body. And so that was about 2005 that I kind of went down this rabbit hole of learning about a lot of, and it's funny, nobody had heard the term biomimicry at that point, but that's exactly what the dental profession was trying to do, is come up with composite cements that would work with the body. Of course, I knew who Janine was because I listened to her. So anyway, I got to move this along a little bit. This is not a small goal. It's a worthy goal. 8% of man-made CO2 comes from the concrete industry. So this isn't pecking around the edges for a couple of carbon dioxide atoms floating around. This is major. It's impactful. It's a worthy goal. It deserves our attention, and it deserves a little bit of research by everybody in the design community. Meeting human needs. I was going to say, sorry, I got to read my own writing here. Achievable goal. I think right now there's a lot of different variations of what people set as their carbon neutral goals, different dates, 2045, 2035. But right now, this is the thing you can do is by incorporating things in non-structural applications, you develop the empirical evidence and trail for the engineering community to follow. Engineers aren't trying to be a stick in the mud and slow down carbon neutrality. They've got a job to do. Make sure buildings don't fall down. That's an important role in society, and they show a lot of integrity about that. So the more empirical projects that can be piled in and reviewed 5 years from now in 2030 will have a huge impact on the adoption of a lot of these greener cements and materials. So that's where I want to jump into this, and I do want to make sure I save time for Lindsay because she's putting it into practice in a lot of ways already. And I also remind us that as designers and builders, we're trying to do things to meet human needs, both housing, buildings, transportation, habitat restoration. I'm involved in a project that's creating a better seawall that will allow the natural seagrass to grow in this concrete lattice work so that the blackmouth salmon can spawn. So then there's more blackmouth salmon for the next thing up the food chain, of course, the orcas, right? It's important. This is connected to the world, our ecosystems all around us. And it should be beautiful, not utilitarian, not some brutalist architecture. And I hear from a lot of people from our side of the sustainable building side of things, there just isn't enough urgency in the world of concrete to convince me that they're serious about this. I got to tell you, that may have been true up to this, but in the last few years, the amount of investment, non-governmental investment, private investment, just pouring into this subject, this is mind-blowing to me. I came up with the first 50% post-consumer recycled lightweight self-leveling concrete. That's not a claim to fame, but I did. I was using a product called Pour River, which is 100% recycled glass, end of life cycle glass, ground up and pulled it, and replaced by volume 50% of everything, and made this lightweight self-leveling. That's back in 2005, 2006. and that was kind of where it looked like, you know, recycled content was a major driver of things. Well, it wasn't. It's now back down to CO2. But the point is this evolution of investment money following us is pretty amazing. So, a project I recently worked on behind the scenes, we were trying to come up with a self-consolidating concrete at the Seattle Aquarium. And what's cool about this picture, and the reason I brought it in, not because I did the mix design with Stoneway, but because you got the main shark tank here in the background, the black, and then you've got the freshwater tank in the front, and the finishes and the structure are all in one here. This is 325,000 gallons of seawater tank and about 125,000, about 70,000 gallons in the freshwater tank. Cool project to have been a part of. And when you think about this, their goal was to lower their global warming potential by 15%, but the concrete had to be waterproof to 830 psi hydrostatic pressure. It had steel reinforcing with a 3/8 inch clearance, so you couldn't use regular aggregate, you had to use sand. You had to have a full liquid head, which means this is liquid from bottom to top in the formwork, which produced 1,600 pounds per square foot. And when you have that much pressure, the sands will want to settle out. We call that phase segregation. And then the exterior finishes need to be free of seams or panel lines, and they also wanted to have it perform as a projection screen. Low carbon cement benchmarks. We right now, as I said, a pretty worthy goal. We're sitting here with a benchmark where it produces 7 to 8% of human emissions. Achievable goal right now by 2030, I'm thinking I can demonstrate to you 60 to 80%. There's a reason I've given a range of 60 to 80%. There are several different calculations, some from the EPA, some calculators like E3 here locally, and they each come out with something different. And I'll give you an example of how confusing this gets. The concrete industry sells concrete by what dimension? Cubic yards. The EPA and everyone else measures carbon dioxide in kilograms. Okay, so when you look at the GWP, it is actually kilograms per kilogram per square yard. What am I not saying that right? Cubic meters. Thank you. When we're going to go into the history here of going towards net zero, there's just a roadway littered with carcasses. This is a good man who's doing good work, but his first time he tried to take on the whole industry, and he failed. I was at the ACI meeting when he debuted a beautiful carbon neutral cement from Calera Corp. It was a calcium carbonate. He was using salt water, brackish water to sequester 100% CO2 from that. That behind him there is actually the last coal-fired power plant in the state of California. Guy's brilliant. He made cements to help bone seal at Stanford Medical School. Met him. I was on his one of his little minions who did test projects with his cement. But anyway, you don't just scale up and go tell the engineering world, I've got the great new green cement. It didn't work. He's back now. He's heading up a company called Blue Planet. So we're going to go through these things. Here's the current benchmarks I think that we should look at. We're talking about the current GWP, global warming potential, with regular concrete in the Seattle area. That kilograms of CO2 per cubic yard of concrete runs about 650 to 789. Industry goals vary. As I mentioned, the National Ready Mix Concrete Association has a net zero goal of 2045. Heidelberg, any updates on that number?
45?
Yeah, 2045.
We have 2030 initiative.
Okay. For the NR, is your company or the NRMCA? Okay. Yeah. So it varies a little bit. But targets right now, just here in the Seattle area, 205 to 330. And this is a very local thing. In fact, even the ACI right now, they have 25 regions of different. It's all about local. What's available? Who do you know? How does the community collaborate? Can you get this cement in the market on your job logistically feasibly? That's a tough question. And so they're actually expanding it from 25 regions in the United States to 50 so that people can work with their local suppliers. Achievable reduction goal right now, with what's on the market and what I will call project ready, again, going back to the lower carbon concrete task force recommendation, we'll call it project ready. It's been proven in lab, it's been proven in field, it's going through validation against code. That's kind of where you want to live, because you don't want to be on the bleeding edge. You want to be on the leading edge. And that's where I'm trying to place this discussion a little bit. By 2030, though, with just what we see on the technology horizon now, we could be very well on our way to a 50% reduction, 80% reduction in concrete GWP. So we're making some, that's very doable. A lot of people got to cooperate. So I brought here 5 materials. These 5 materials here, which I'm just going to run through real fast. These are all plausible and available. First of all, you've all heard of type 1L. There's also type 1P. The P stands for pozzolan. The L stands for limestone. In essence, these are added and blended into the Portland cement to produce less carbon dioxide total for the cement without decreasing the cement strength. There are differences, though, and there is pushback. There's lots of people saying they got a problem getting it beyond this range of 11, 15%. Most people here in Seattle are running 13.5% limestone added. Does anyone have any questions about what that means? Adding limestone into your Portland? What that means? It means a slate limestone that's been dried but not gone through and released all the CO2 is blended into the Portland cement. It slows down the slitting of the cement a little bit, but its ultimate strength is equal or higher in lab. In practice, it changes some of the mechanical properties of the concrete, and there's been some questions about, can you get to 30%, and how far are we going to push down this road before it's not concrete as we recognize it? So I'm working with a lot of people who are trying to look at the stuff. Even the school here, Mike's group, has opened their doors to looking in this issue. So,
can you use that in addition to fly weight or fly ash?
That's a more complex question. There's 100% slag cement formulations that don't even have any Portland cement. But commonly, yes, that doesn't interfere with putting in slag. Fly ash, same thing. Doesn't really change it. At these current levels being 10 to 15%. Okay. What will be interesting is they're doing test pilot projects right now at 30%. And I think there's going to be more questions. What happens then when you add in things? Okay, so that's available anywhere. Again, I bring up everything here is available in the market, and I printed out the contacts for all these materials so that you can get that going if you want to work on it with a project. Calcium carbonate cements. Calcium carbonate cements, basically limestone is the calcium carbonate cement. It's a big category. It's not simply CaCO3. It takes a lot of forms, and this particular one that we're looking at here is called Vaterite. In nature, Vaterite is a very tough calcium carbonate. There isn't enough of it to be an abundant to scale up and replace cement in the concrete industry. So they have figured out a way to synthesize this process and make Vaterite cement. Pretty impressive. The mineralogy, I use the same format for judging all these cements. It's not a perfect way, but it's I should say, I have zero conflict of interest with anything I'm talking about here. I'm not on anyone's board of directors. I don't sell this stuff. I have no connection to any of it. But I try to kind of lay it out without saying pros or cons of these things, because they're just that they're available and they're viable. This one is good. It's a little low on the compressive strength at 2,500 to 4,000. It is giving 60 to 80% reduction in the concrete's GWP factor. Its inertness and chemical stability is good. I went, good, very good, excellent in that rating. And the only reason I went good on that is there's just not enough empirical time to judge these products. The cost range on this is 180 to 250 a ton. And this is important, everyone should know, regular concrete. Oops, went too far. Where do I go backwards? There we go. Sorry. Regular concrete Portland type 1, I put the cost range as 190 to 220 a ton. Big difference between whether you're buying silos of cement or or a bulk sack or a little tiny 50-pound bag. But keep that in mind. It's important to have a relative idea of how much it's gonna add to things. This Vaterite is running about 180 to 250 per ton. Its availability, there is no feedstock limitations, but it is made to order with a 2 to 3 week lead time. We have two resources for it. We have Lafarge, and then they have Forterra. Next is a ceramic cement. Ceramic cements are essentially cements without any of the limestone components. So the majority of these have been around for a long time, from everything that the early humans used to make plates and cups and bowls. The mineralogy is a phosphate plus some oxide, either a magnesium or potassium oxide generally. Compressive strength on these, and this is why this deserves conversation point, is these things are bondable to anything. Bondable with wood, bond onto each other, bond wet to wet, bond wet to dry, bond to metal. They have radiation shielding capability. They've been used and studied at Hanford, and they have a strength that comes in at 5,500 PSI at 3 hours. So if you need something rapidly done for strength purposes, this has got to be in the equation. And you're still reducing your GWP by 40 to 60%, 65%. When you do their strict math on their calculation, they convince me it's 65%. But what that doesn't take into account is what the rest of your concrete mix design look like, your aggregate and transportation. The inertness and chemical stability is excellent. This is the same type of system that you use when you get a composite crown on your tube. Cost range of this is expensive. It's $1,800 to $3,000 per ton. Now, that said, there's something about that. The majority of the 500,000 tons is waste in brown sites over in eastern Washington from World War I aluminum and weapons production. So the cleanup process, state is tagged, State Department of Ecology, includes cleaning up this site, and this stuff is ready to be turned into cement. Anyone have any questions about that? Yeah.
Will that cost, relative cost, remain that way, or is that a time limited?
That is today. I'm not giving scaled costs for the future production. I was just
that issue you brought up. Like, is that just a now problem?
I think yes. I think when you open up the what they call the dead burn MGO, and you're saying people this is free, you just got to clean up and do a reclamation of the site. That changes the equation. There's no processing of the dead burn. It's called dead burn MGO. You can look that up if you're interested. It's an interesting thing. What's really interesting is just this is a really great cement for wastewater treatment. You don't have to worry about microbial action from sulfur dioxide. It's a stable cement system, and it's been around for a while. Any other questions on that? Okay. Here's a cement you may not have heard of called sulfated slag. So we all know what slag cement is, and it's a byproduct of steel production and other metal production. The various constituents of slag cement are all over the board. Their reactivity levels all over the board. Their ultimate strength of what they do in concrete all over the board. This is a little bit more interesting because what they did to reduce the CO2 in the process actually made the product a little more stable. And this is 100% replacement for Portland cement. It's been used on Target and Amazon projects here in Washington. It's moderate cost range right now at $600 to $800 per ton. There is no feedstock limitations. I question maybe whether that would change if it becomes very viable and generic, but for right now there's not. It's a 2 to 3 week lead time.
Just sorry, if you go back to the bottom right there, what are those three little paddles there?
Oh, that's
I can't read it.
Yeah, those are just some cement samples that were polished up.
Okay.
That's all. Yeah. And this is a bridge here in Seattle. I just threw those photos in because the project I'm involved in. Not that good. That's integral color. Yeah, the natural color would be that one right there.
Okay.
Yeah. Finally, this one's not a cement, it's a super slag. Or excuse me, super, I didn't have a category for it, so I called the zeolite guys. And I guess because it has an improvement in reactivity with Portland cement and plays well with it, it's a little different than your typical SCM is fairly neutral, right? It might improve workability, but it doesn't really improve performance and durability and strength. This particular SCM does, called Zeolite. You're going to hear more about it. They might have bigger future plans, but again, I'm trying to keep everything here and now. What is available? What do we know? It's up to 50% replacement of Portland cement. That's a pretty good reduction in your CO2 content of your concrete. Global warming potential production. Oh, it does that. It does that, and this is important, without compromising no diminishing returns from the strength on your concrete design. So if you have a 6,000 PSI structural concrete mix and you put in up to 50% zeolite, you're not going to see a change in your 6,000 PSI structural. Wow. Okay, inertness and chemical stability on this is very good to excellent. The cost range with freight to get it here is about $125 to $175 per ton, so it's less than Portland cement. No feedstock limitations. It is made bagged to order, I should say made to order. The natural material is just laying on the Mojave Desert floor, so it's not like it's manufactured. It's just a matter of getting it here. Contacts for your project-ready low-carbon cements are here, and I've put this onto a one-pager for everybody. Contacts. Oh, then I'll say this, and I didn't know Heidelberg will be here, so I'll probably never be employed by Heidelberg, which is unfortunate because they're an awesome company. Yeah. What I was going to say is, don't let perfection of being net zero and going as fast and aggressively as possible get in the way of doing something. I want you to know a lot of ready-mix people aren't going to be really thrilled about cleaning out their silos and throughput mechanisms to load up your truck. So if you got a project that's 20 yards of concrete, 30 yards of concrete, you're going to get charged for that if the ready-mix guys really want to do it. You might be better to look at your other mix options. And I'm just going to run through a few of them again, trying to be practical. Yes?
Yeah, you're talking about the currently available mixes that you've heard of, like brimstone energy, calcium silicate, 100% offset supposedly that should be available in, I don't know, the next 5 years.
No, I definitely have. And I definitely have a list of about 100 things that would be very fascinating to talk about. But I needed to say, I took my criteria to being project ready and available in our market here now. And so I didn't get on my radar.
Any, like market leader, or is there any specific like single mix that you're most excited about?
I think the final mile of this thing, we're gonna march down the carbon dioxide 60 to 80% like I predict. I'm pretty confident of that. I think the final mile of net zero is going to require some kind of carbon capture technology, and it'll probably be in the aggregates, is my guess. To look at like what Blue Planet's doing and Carbon Cure. I mean, people are trying to figure out how to replace some of the sand and the rock. Just keep back to the basics of cement, sand, rock, and water. That's how you make concrete. And the rock doesn't really add much CO2 to the equation. It still has to be quarried or recycled, which takes energy and transportation. I think that's probably where it's going, but it's going to require some carbon. Again, I hear these talks and people get really sexy photos of things that have great potential, and I'm just trying to put it on the table here and go into practice with things that are meaningful. And again, if we meet back here 1 year from now and we take stock of where this forum has gone, what's been done, what projects have been done, how much did we reduce CO2 on these projects, we're going to be pushing some great numbers downward a lot faster than the people who have their timelines of 2050. And that's kind of like what I'm talking about. I had to, for the purposes of advising people who are working with these low carbon concretes, what can we make now? And it's not even easy. I just run through it. This is a small mixer for these are alternate ready mix options. By all means, call Heidelberg or any other big ready mix producers that we have here: Cal Portland, Stoneway, Miles Resources, even San Beda, Sand and Gravel. They're small, but they're all. I got to get the people, Yeah. But if you want a site portable mixer for doing little batches, like a half a cubic yard to up to a year, I'm talking per batch. This is a small one. This is cheap. If you have something mixed in kind of the 1 yard to 10 yard range, these are mobile mix trucks where all the things are in the compartment and allows you to do up to 10 cubic yards per batch. This is really great because on some sites, you're not really close to a batch plant. This can go anywhere, and they don't mix it till they get to the site. It increases your cost factor about 20% over the batch plants. And finally, there are some independent ready-mix trucks. These guys generally will get their aggregates from whoever is the local aggregate supplier, or will have an agreement with somebody. But the people I talked to on this particular issue were happy to take a super stack of any of these low carbon cements, dry batch it. So that means the truck has to be dry inside, dry batch it with the aggregate, and then add water at the appropriate time as it gets to the site. And these are the contacts and companies in the small, medium, and large mixing world. And I'm sorry to have spoken as long as I did. There you go, Lindsay.
You're good. I think you're good. Thank you, everybody. My name is Lindsay. I'm a landscape architect, and I started this journey, started the firm about 3 years ago, and really put into sort of practice over the last year after kind of going out and trying to understand it myself. So the title of this is like Site Features 2.0, rethinking some of the things that I have to deal with in the landscape architecture world, which I'm so excited because there's so many different professions in this room, and part of the journey really has been learning and meeting new people along the way. I got to figure out which direction this goes here, or where I point it.
The top arrow is forward.
That big one. Got it. Okay, so real quick, this is me. I own Scapa. I have 25 years of experience as a landscape architect. Some of you I know. After that 25 years, I just really kind of looked at what is the idea for the firm, and I wanted it to be different. So I've taken this firm and flipped every single thing around based on my experience in other firms, and I've run and managed and stuff. So that's the idea of the firm, is to really look at things and do them different. It's not like one project. It's how can the firm do things different. So one of those components has me looking at technology in a way. I mean, we've all seen it online, but really wanting to see technology and innovation. How could I achieve maybe moving down like the green sustainability and really feeling good about some of the things that I was able to produce. And along the way, these kind of are the questions that I sort of discovered, and I broke the presentation into two parts. One of them is how could this technology actually be implemented, and then the other is to kind of explore some ideas of actual projects that I've been working on. Along the way, all of these things come up: the new relationships, the design freedom, new skills, green workforce development, sustainability, and new materials, which Dave really landed on. And getting to meet people like Dave to help me understand some of these mixes and really just move things further along. It also kind of made me rethink how the office is, and maybe that in the future there's some other positions. So you can all probably relate to the first three, the landscape designers or junior staff coming on. They're also coming in with really heavy modeling skills and maybe less blueprint and plan development, but more modeling. You get to your landscape architect and project manager. And then I've kind of added two spaces to the firm. One is called a blender and the other is called a slicer. And this is probably recognizable to a lot of the architects and designers. And the other piece of this is, like, everybody in this room can accomplish these things now. We're already using these tools in our offices. And so part of that is showing how you can do this. This is a typical workflow in a design office: CAD, modeling, going back and forth between the two. So this is what we're looking at on our screens. The idea of the blender, what I call that person, is someone that's more likely to be in an architecture office, a design office. They are working on the modeling and selling the clients and Lumion and all these really, all the renderings that you're seeing for all this. But they're also very knowledgeable about all things 3D. So you might be looking at a master plan, but you see something like this where you have components. I'm clearly looking at the landscape, but finding components where maybe we can implement other technology to accomplish those. So I see that Blender being able to understand this. They also have to be able to now talk to the slicer. And the slicer, I envision as somebody that works for a general contractor out in the field. And this is guaranteed the new layout, right? We have actually put a Sharpie in the machine and drawn the layout, but the field is going to get your file and they're going to run a dry run and you're going to hope that it works. And if it goes way out, they're going to call back the Blender and ask them to fix the file. But if you have a slicer should be able to deal with tolerance on the site. It's never going to be a flat site. And these are actually things that you'll see. So the slicer would see, the robot will actually tell you whether you're off or on, but you're wanting to read that. You're also thinking about construction management, how you're going to print these. So you know about the space. And so from here through the next few slides, I'm literally taking you from the process of when you see it as a designer all the way through to the implementer. So these are typical Rhino models that we use. We go from Rhino into the machine. This is a typical, okay, so you're a designer starting to work in SketchUp and you're thinking about these things. As you move into the development, you're starting to think about printer paths and layers and all the different things you want in a design, and you're starting to implement that kind of in your blueprint phase, the next CD set. And then you're going to start to see these visually in your models, in your technology, cooling for my office, seeing this all day, speaking with the slicer, understanding how much material, how long it's going to take. All of these things are coming into play. You're also designing and thinking about these things too, whether they're realistic or not. And we might set up and do all three of these in the day. You're going to want to kind of understand that. Anyone who works with concrete knows that. The next step is obviously it gets out on site. So here is where the journey collides with this building in the local 528. Because for me, I can only do so much. I rely on the craftsmen and all of the construction to actually implement what I want to do. I am so grateful for this relationship because I don't have to worry about quality. I know that they don't want something to fail. So if my designs are being built by the union, I feel like they are really putting in all the effort that I need to actually construct it. That makes me feel very confident in trying new things. So on the left there is Jordan. In the middle is cooling. On the right was Angie from the robotics company, all working on this the first day. Jordan worked on the robot from day one. Like everybody was able to use their skills that they already have on day one and show up when this thing showed up here and undid it. And that was, eye-opening to me. I mean, it takes the whole team, but it was very easy to accomplish. So here's a picture of some live printing in a shop. As far as technology goes, I would say that the South Seattle College, some other, I've worked most with some of the community college. They're really teaching the actual technology of the robotics. That's where I'm seeing it. And they're the ones printing things. You have to have a guy like this to trust 100%. So this is us doing a little bit with the union and then doing the mixing here. And then on the left is the robotics technology there. It is a 6-axis arm robot. It's a KUKA. That's not the proprietary piece. You can find KUKA doing everything in factories. In fact, it's bagging the cement that you're buying in the factory. It's crazy. The proprietary part is the actual kind of slicing and the actual putting it in and it reading it and printing it out. And so that's the thing that you have to learn with the actual robot. However, I still see it as a tool. It's, you know, no different than a tractor once you get used to this and what you're using. An architect or a designer would still need to know whether they're going to build it with that robot or a big gantry system. That would change things. But outside of that, you know, you're specifying what to use. And then another big important feature to me was, I know that the layered look would be not for everybody. I have a lot of high-end clients. There's no way that that bathroom that Kohl's did in layered concrete, that any woman would ever want to go to that bathroom. It looked like it was in a garage. And so part of that was for me to help say, you know, I've got to make it for everybody, or it's really just something I always have to sell. And so that's where the Plasters Union came in, Cement Plasters Apprenticeship. So that's them on the right finishing it. We're going to walk around and see a lot of these finishes, but there's exterior finishes, interior finishes, more than I could have imagined what they did. Finishing it with the material that was left over. That's what this one on the left is. So the left is kind of a layered look. And then right next to it, they finished it with the Sika material, just excess material. So, and then on the right, a Venetian plaster. Robot, I show this picture next because it's the mixer, and really that's kind of the key to some of the next slides that I'm going to go over. And then this is really, depending on where you are, it's the future here. It's actually happening in other parts of the world, right? I'm showing a lot of things in the shop because I see myself as kind of wanting to play around with it. I'm a landscape architect, maybe I can hit smaller features, but ultimately there's things like this going on and have been part of prints this year where they completed a Walmart. So there's very large scale projects going on. Walmart, I think they did it in 7 days, 45 days ahead of schedule. And so practicing on things like this, I don't think this is far from the future. With that Walmart that they did, they had a 4-man crew on 2 robots. And so they just kind of move around those 2 robots. Which gets me to thinking about actual green infrastructure and projects. And so that's this section. So you see kind of the process, how you get there, and how everybody's involved pretty much in this room should be able to relate to one of the earlier slides as to what they might be doing on a day-to-day basis. But I really wanted to reevaluate like what I do in the landscape. When Dave started off and asked everybody in the room to name off pieces of concrete that wasn't structural, you know, some of these are in this. So I took kind of like this look at reimagining concrete and features here and maybe making them more artful. So this picture is showing, you know, your typical stormwater, like beehive drain down there, and cast in place concrete, precast concrete, typically definitely not something anyone's going to go and look at and enjoy. However, maybe they could. Maybe we have some more artful features and habitat included in these things. And I'm just looking at ways to not only solve, you know, carbon, but also solve many problems with one piece. And how many more things can we do? This is another idea where I started to kind of pull across pieces. I'm using low impact development standards that are set forth by the city as kind of my guiding principles. So if I can show the city that it works and it holds water, I would call it a bioplanter. It would maybe or maybe not meet their standards, but I'm trying really hard to show that it can. So this was kind of rethinking. This is a project in Greeley, Colorado, where we're doing some low impact development. I'm implementing some parts of this, not all of them, but but the idea of just being able to like implement small projects with a smaller workforce, or even do this in a shop and then bring it out to a site and drop in stormwater planters. Those are the kind of things that I'm looking for, like the low-hanging fruit. This is a stormwater planter that I printed. It would have met all the standards for like a City of Seattle project. It was modeled after a house project. You know, the city's requiring that much biotension, and obviously we have a general contractor. It's formed. It's, you know, all kinds of work and effort and waste goes into it. They're big enough to where I could almost put my truck in it. And so I'm thinking about ways to just do that less. It's a 4-inch wall minimum on either side. Here I'm doing it with 2 inches, a lot less material, and can be delivered to the site. And this just shows how it might be thought of. This is another concept, probably something everyone's familiar with, the bioplanter, the non-infiltrating bioplanter. I just love this idea of, A, they could be beautiful. This is one that we finished. This would have met the City of Seattle standards. We did a double wall just to get the thickness, but I also could envision this as a spa and being able to insulate these pieces and things like that. We finished this one, but I think this maybe it took us 3 hours to print something like this, and to be able to do something like that with formwork, we didn't have any waste, something that could be dropped off on site. This gets down to a little bit of an idea that I started to think about, which this was the first slide, and then I met Dave, and the next slide is one of my like the more exciting slides. I call this, for better or worse, I'm calling it the wet rat slab, just because I have this idea that it could come in and store water and things. I'm being told by engineers to hold water on site, et cetera, et cetera. You know, we're always doing like a regular 4-inch slab, but if an engineer told me something and maybe I needed to do an 8-inch slab and manage all that water in one place, I would be doing more than one thing and solving for more than a few problems at a time. You know, filling these with some sort of water quality material like pumice or any of those things where we're just asking to kind of go through water quality on the site. They're all things that we have to do every day. And then this is somewhat of a like reimagining the curb, right? Why does it even need to be a 6-inch solid curb? What if we could just continuously pour these things and they were more like a green curve that managed stormwater and then passed through it? So these were some ideas that I was generating. I also have, I do a lot of high-end residential. And so, you know, as much as I want them to want this, my clients don't usually want to go from their 2,000 square foot onto permeable paving. And I'd really like to find a way to solve being able to make something permeable, but also being able to use maybe more high-end materials to do that. So this idea that maybe I could bring water to a drain and then underneath in the slab, I feel like I could get a lot farther in some of my designs. And then I met Dave. And Dave had this crazy awesome idea that I really loved about all these mixes that he just went through and spoke to. Because the technology allows us to put additive in right then. Like, you know, one day I hope to be able to put waterproofing in there and not ever need waterproofing if I did a container or a spa or a bioplanter or water feature. But this takes it to a next level because with that technology, we can switch things out. We do color, we do different things like that. But the different colors that you're seeing here, the idea that we could do the orange, you know, something kind of more structural, almost like a little bit of a formwork, load-bearing pieces would still have this high,
So they had that ultra
high
Yeah,
performance.
you're approaching 18,000.
Right?
Incredible, 20,000 PSI.
And then even in the same design, be able to switch it into something like a mortar mix where we're more, CO2 neutral or something, to be able to actually change while you're doing these kind of construction things. That's kind of the thinking. Also, we know we have permeable pavers, but a lot of times the permeability comes from just the slot, right? And so the idea that these pavers could maybe be porous and also water cleaning on top of things like this, and somewhat of a semi-pervious, wear tread on top of something like that in a parking lot, versus using monolithic everything all the time. Rethinking the site wall altogether. I am asked to calculate impervious surfaces for things like walls all the time, and you think you got it all down, and then you go do the calcs on your wall, and goodbye wall, something like that. So this kind of thinks about it differently. It opens it up to maybe being a planter wall, could also be a bioplanter, but just the idea of being able to retain something and plant it and not use it as monolithic, especially on, the 4 feet and below, the landscape features, this idea of rethinking the wall. Obviously, I can have a lot of fun with my designs. None of this has any elevations the same. It's built to kind of segment and go together. So if you wanted to have this on a project, maybe you don't have a general contractor, but you still would like to have concrete on the project. This is a chance to kind of do more custom features for people without maybe as much expense. I'm also looking at, in this situation for a small wall, why even have it be 2? Why couldn't it just be 1? I mean, you're going to go out there and you're going to see it, touch it. You can imagine just having a little smaller planter wall, and that's it. We did a lot of different finishes here, so this one gets turned around. This was another idea that kind of has started to generate. So now I have this gap in the walls. I can plant them, but I can also start to think about integrating passive, or, maybe it's not passive, but somewhat of a mechanical, the opportunity to maybe have a misting system inside these things with irrigation. I'm already doing irrigation, lighting. So this was like a little bit of an exercise that we did for the Seattle Design Festival, where we thought about walls. We all know we got a park, we put in lots of trees. That feels good and cool, but also this opportunity to maybe have, site walls that go throughout that can also kind of cool you off. So instead of a fireplace, a cooling place. That's what the tower was on the left. And this is here. So we actually did build these with high school robotics, Montlake Terrace High School robotics team. They just came in 16th in the world at the robotics. I engaged them to help with this. By the time I was done with this introduction, they were already modeling it on their computers. They're very, my intern gets dropped off by his mom. It's awesome to incorporate that into this, thinking of hiring different people and asking different people to help. Climate resiliency is obviously big on everybody's mind now. So this was a chance where we invited the fire department to come and give us some data, because to be honest, the insurance companies don't really have the data. I mean, you can kind of sit there and stare at it, but they don't really have it. So we're trying to actually build things so that they can come burn it down and have it. And ideally that starts to get things into code, more acceptable. The things that have been kind of built to code today are basically off the masonry. Like, they're following masonry code for the most part. So we do use reinforcing and things. This one is one example of many ways that people have really solved some of the reinforcing. But this is a threaded rod, so you're able to thread it up as the machine moves up. Got its top and bottom plate. And then we're also just pouring the column into the design. So the design is part of that thinking as well. And Jordan back there, when we go walk around, I hope you get to see it. There's idea about skeleton footings. We have a lot of cool names. Wet rat slabs, skeleton footings, things like that. This one is kind of for the architects and everybody, but really it's wanting to show how, this process works. We're going to go and do custom features for our clients, and then we're actually going to be able to print these pieces here and finish them the way that we would want them finished anyway, and drop them off. No form work, and ideally using low carbon concretes. I have printed mostly with Quikrete and Sika. Sika is low carbon concrete at the high end of that range, but the opportunity to do things in the landscape with different mixes, things we've achieved in the design. That was like a barbecue fire, outdoor kitchen type situation. This eventually gets rendered and has become part of the gallery out here, but I can see that as water feature wall or some sort of screen, and it's open cavity. So the reason I end on this slide here is because I am here to say, a lot like Dave too, is that, I'm not necessarily here to preach. I am not necessarily here to teach, even though there's components of both of those things. I really am here to coach people in how to use this. And I've gone through it. I believe in this. I see this as a way for me to maybe bring it to others. In my mind, this is my ideal shop where, you have a gallery, you have the design office, we have the robotic construction shop, and then even the idea of maybe having finishing bays outside so that any contractor can come. I mean, it's a lot to ask someone to invest in this all in, but if there's a chance for me to hey, I'm a small firm, can I implement, the signage at the convention center project that I might not be able to win? It's a chance for people to try it, learn it, feel comfortable with it, use it when they can. Bring your own files down. I mean, that's what I ideally would like to do. I have spent time now in every one of these stations and feel very comfortable with the technology and just get really excited about it moving forward,
Materials lab is where?
And next door.
They come perfectly ordered. And I look at this, I have this little kind of ordering, stop here in a second, but, the idea that you could come and maybe have an economy mix that's still green and sustainable, people are able to meet it, anyone could use it. I personally don't want to work with DIYers necessarily in the shop. I want to work with all the pros and really make amazing things. But, your kid is already modeling it and maybe they have a cool model for something, or you want to just use a lower price. I see that as an economy mix, and then it goes up from there. And things like Sika, maybe that's an architectural finish, and you're paying a little bit more for that. And we're just going to keep adding color, all those things. I don't know where my color slide went, but we're playing around with color. So that's yeah, I'd be down for questions.
What kind of concrete mix do you, how much, GW, how much global warming potential reduction?
I have no idea. When I started this, I would never be able to speak like Dave and all this. But I've been able to look people in the eye and say, originally I used less, right? I start with using less, and it only gets better from there, in my opinion.
Yeah, I don't have an idea where the Sika mix is. The Quikrete formula I know a little bit about, and it is using type 1L cement and a calcium aluminum cement, probably running about 20% less TWP. I don't know their number though. I'm going to guess to that 500 kilograms per cubic yard.
And they do make mixes specific for 3D printing, so we're not out there just making it ourselves.
Well, that's what I want to understand. I mean,
You even said it, your traditional thing of concrete, you have big rock and gravel, and now you're printing with basically sand, with mortar.
Yeah, it's structural work.
So how does it differ, like, if you use that same mix as your normal pourings? Like, what's the difference?
No, it's got a particular rheology that as it lays down wet on wet, it keeps its dimension in the way that it's programmed. And so you can't have variation at all. It would change the hydraulics of the feed. You've got to hit a particular target.
comes out.
It's not necessarily more viscous. It's just the consistency is a very tight, narrow range. Don't want it too dry, and you certainly don't want it too wet because it won't stand.
So you
Right.
mix it on site,
Right.
hopper behind the machine. You have to be very, very, very careful. Don't screw up the mixture.
You do your water ratios and everything. The cement masons here deal with
Yeah.
technical grouts and technical self levelers and things where you got to be a very narrow range, like plus or minus 1% on your water ratio.
Yeah, so it's
That kind.
very, you have to have like scientific love and something and stuff.
No, you just have to have processes. You just have to
Yeah.
have really good measuring processes. That's all.
Up in there.
Go ahead, Mike.
You're right. 100% right. And materials and things that we work with when you take talk about the API stuff, there's technical dash, tried and true processes on how things work and stand. So the idea is where traditional high slump concrete and low slump concrete, where you have that wide range where you can work it, has been narrowed way down to a tight window, but it can be very proficient. And it's allowing, what's neat about this arena is, I heard someone's here from Baylor Driving with hemp. They have printed with hemp, structures with hemp in European countries. These windows with opening up and 3D printing the options of more low carbon materials and using natural resources in that area opens up a different window. That is very calculated. And I'll kind of go into it a little bit, but that's kind of why we're all involved with this, because we're very familiar with this. And we've watched people burn hundreds of thousands of dollars trying to run equipment and materials to get through this process. This is nature to us. I can do this in my sleep. I'm not bragging. I've done it for over 30 years. I had over 100 years of people giving me experience. So we're here to try and we promote that. So I'll just kind of go in if you don't mind, John. That's part of the reason we're here involved. We believe in technology, economics, low carbon. Unfortunately, I have made a good living in an industry that is polluting the world. I can admit that. But it is a structure that has to be done. This is what the world's built on, is concrete, right? So I'm excited to know there's other partners in the industry to help produce these structures we need and more environmentally friendly. And we all need to collaborate together because we've got workability and finished product in the end. Because we know lab results are completely different than real world results. These comments were Dave asked where some low structural projects that can be done. These are projects that can be tested real world now that can promote more people to be involved, more industry partners to help move things along to a higher volume level, or we have to start small, right? Be it our sidewalks, our planters, our bioswales, 3D printing, all these different options that we have. Right? And so we're excited to take part of that and help bring you guys here and be a part of collaborating to help better the system. Sure. And stay in that tight window, because if we fail, the world's gonna say that doesn't work, and now you're home, right? Hey, Mike, give this a minute, and I think I'm sharing this on the screen. You or Jordan could say what we're seeing here.
Oh, you got it. All right, Larry. So when we're here, that's our shop. So we become partners with Lindsay, and we're working with Zeolite. They're ones that have helped us with some products. And there, of course, Dave is a long time part of our training facility for over 30 years now.
Yeah.
I was an apprentice learning from him, but, we're trying out materials, seeing how it works here. Here, we're with another group and showing that the, ability and the creativity of material. Now, if this is a concrete structure, we're creating a bench here that's arched with less material, so that's a good thing there. There's zero formwork, which is a good thing for saving money on waste and other nature acquired components that as a human beings, unfortunately, you all know we are all consumers of natural resources. So here's a way to limit those resources and the production of making those resources. Great concept.
Question, one last question. I should statement, just occurred to me.
Form of oil, the fuel it takes to create all the extra formwork that gets wasted, burned, thrown in the air. I mean, there's just so much that comes to it.
I would remember how much lumber.
Yeah. So I wanted to stick in my lane on the cement chemistries, but 3D printing is my point of it. I mean this, concrete is really in its infancy. Yeah, concrete is nothing more than a sophisticated brick. The way that we use concrete isn't really how it was born to be used. And what I mean is you go from the stones of the Egyptian pyramid to bricks of later centuries, 17th, 18th century. And concrete was just an extension of the brick. Because how do we form and cast it? We cast it in sheets, slats, columns, beams, right? Walls. It's all rectilinear. You all of a sudden, and people have tried forming systems that are not rectilinear. They've tried canvas injection and all this stuff, interesting serpentine and curvilinear, but 99% of it is linear, rectilinear design. And all of a sudden now, the 3D just unleashes concrete's potential to be a lot more. And even more importantly, like she was showing the simple catch basin of the pot. Imagine if you have a concrete that's super strong, a concrete that's pervious, a concrete that's semi-pervious, a concrete that's net zero or negative carbon, another one that's lightweight. Your injection allows you to alter between all the design performance features that you need in the element where you need it, instead of one monolithic cast and one mix. This is groundbreaking, because now concrete can be very efficiently used, where you could have, beautiful spherical, curvilinear buttresses that are structural in combination with the same chemistries that make it lightweight and give it a diaphragm. And I didn't want to get into that because this goes along the theme of what I'm saying is concrete still has a lot more to grow from its kind of brutalistic column, beam, slab mindset. Pretty cool.
I never did forget the RFI that I got that said this design is too curvy. It still is in my mind. That was my answer. That's not a question. Yeah. You bit it. Not my bad.
If I can reiterate, so I was looking at a study that was taking place in Europe, and it was the skeletonized structure of a footing. And what this person was able to do was use, I want to say it was a third of the material in order to create the same surface area, because you're not limited by this form. And so not only are you not using forms, but you're also amplifying your surface area by being able to print that skeletonized structure underneath and being able to compact that into gravel or dirt or whatever you're compacting around it, and being able to get the same load levels as you were able to get with a normal structural footing using 3 times the material. So it's pretty amazing what you're able to do with the technology. So,
Very good. Any last questions before we move on?
Just a really quick one. Do you have any machines that fit in a 3 to 5 foot clearance to get to a backyard?
Yes.
Oh, yeah?
Yeah, the smaller ones do that. And you're going to see that over time. Right now, it's interesting. The robots are using parts from the concrete industry that they can find. But as people start to develop parts for this, yeah, I mean, There's small ones that go in. There's just the one arm that you can bring in. They range. There's a whole range of sizes, but
These would be great questions too for when you come to the shop.
yeah.
So there'll be a whole bunch of us that can answer a lot of those off the wall questions that you'd be amazed on how.
Can't fix that off the wall.
Yeah. That's my everyday life.
Off the concrete, off the 3D printed concrete wall.
Yeah.
Those questions are outside the square box.
All of these questions are outside that, right? Yeah.
This question, thank you very much. Thank you.
Thanks, guys.
Anyone that wants to have real information and contact, sir.
Thank you so much. Our next speaker, we're gonna have Neil, Armoron. Well, Neil's setting up for the second time. I'm gonna start passing this around. This is actually, whether it's poured concrete, 3D, we are working on a low carbon 3D mix, but this is an ultra low carbon paver, 9,000 PSI.
Okay.
So have you ever been in one of those meetings where you have to follow somebody, you're like, oh my God, I have to go next?
Yeah, so I hopefully will keep this short and sweet. I encourage lots of questions. If we can't do them here, we can do them on the tour, or you can follow up with us afterwards. I know that I'm standing between you and some fun stuff later on. Neil Amrine, based here in Seattle. I'm really excited to be here. I'm thrilled that my partner Dan is with me. He's passing around a commercially available product. We're using this in projects in Seattle right now. And so along the theme of what's available today that will make a difference in our climate, in our carbon footprint, we have finished products like the hardscapes. We have ingredients to cement and concrete like our powderized zeolite, but the entire business that we're running, Zeolite Composites, revolves around this technology. It's effectively a mineral called zeolite. And zeolite's an amazingly effective replacement for cement, whether it's at a batch plant, a small mixer on your job site, in a hardscape finished product like a paver, you name it. We're bringing the carbon footprint down of concrete immediately, right now. And the product that we're passing around in the back of the room, compared to a OPC baseline, there's 50% less carbon footprint in that product. Quick show of hands, who knows about Built Green, has used their checklist? I see a lot of hands here. So we're actually going to be going through our first couple of Built Green projects this spring and summer, including verification. And so very quickly, these projects who are scrambling for points to get the silver and gold ratings are going to be able to accumulate many tens of points by simply swapping out legacy products with these pavers and reap the benefits. And so it's a win-win for everybody involved. Let's see if I'm going the right direction here. Let's see. The big one is forward, maybe? Working? Not sure. Let me find it off. Click there and make sure.
Tell me to advance the slide.
This one I think Dave covered for us. This is the history of concrete. We're going to leave this as a resource afterwards, so you guys can go through this. But effectively, we've been using concrete for a very long time in a very similar way, iteration after iteration. And so it's recently that I think everyone has shown interest in trying to attack our climate crisis through improvements in concrete by replacing the dirty ingredient, which is the cement. And so lots of technologies out there. We need all the oars rowing in the same direction. But some are going to be more scalable, more cost effective, and more impactful than others. And we have an ingredient, the zeolite, in our zeolite composite in our finished products that are available now. They're going to have an impact, through these different brands that we've operated. And we're on the road to, hopefully, in the next 6, 12, 18 months, a carbon negative solution. And so we're really excited about the opportunity of building products that don't just eliminate carbon dioxide from being created in the first place, but actually acting as a carbon sink and going through a carbonation process to pull carbon dioxide out of the atmosphere during the curing process and life of these finished products. Oh, sorry.
And now it's working.
Yeah, now it's working. Real quick, zeolite is a naturally occurring mineral. It's a rock. It's a very soft rock, but it's a rock. This is a rock that we pull from our source in Mojave Desert in California. We are a vertically integrated company, and so we have control of the source, tariff-proof source, I should say. And with very light processing, basically electricity in a mill, we're able to produce the format that you see here on the table. No energy, effectively, no kiln, no clinker, ready to go replacement for cement in concrete applications. And so as you start to look at the universe of FCMs, we consider ourselves being part of that family. You have a whole range of things, including things like slag and fly ash. I'm sure a lot of you here in the room know that these are resources that are dwindling in supply, which means they're getting more expensive. So as you start to look at cost today versus cost yesterday, cost tomorrow, it's almost a straight line up and to the right in terms of the cost of these products. As you're thinking about ingredients that are trying to help improve the performance and effectively the price of the finished products, there's going to be a very tough conversation coming soon, if not already, around what do we do? How do we make our concrete cost-effective, greener, and available into the future? And so that opens opportunities for solutions like ours to enter in and provide a multi-dimensional solution to this very complicated multi-dimensional problem. The key to our solution is not just that it works as a cement replacement, it's an effective cement replacement because of the natural characteristics of the mineral itself. And so for those of you who know some of the keys to making cement work, it's the silica to alumina ratio. It's very important. The higher is better. And our clinoptilite zeolite, naturally out of the ground, has a higher SI to AI ratio than fly ash and slag. It's almost twice as much. So as you're thinking about the effectiveness of these FCMs, this is a key consideration, and why there's a lot of limitations with the vast majority of other options on the market is because they can only perform to a certain level, and then you're tapped out. So what do you do next? And so we help you kind of jump that hurdle and get to the next level of performance with the Ultimate Concrete product. I think we're going to zip through this pretty quick here. Yeah, no problem. Right now. Oh, there we go. Okay. This is a fun leave behind. We created a couple animated videos to talk about what is zeolite, where it comes from, how it works, and why it's such a good replacement for cement. And so we're really excited about the opportunities with pavers in individual yards, personal choice, but also municipal projects and also larger scale projects as well with other partners, rapidly removing carbon footprint from ultimately these things that get put into our environment. And I think we all have a shared responsibility of making good choices, both for ourselves, for our neighbors, for our families, for our communities. And these are small steps we can take with readily available solutions that are on the market today to drive these rapid changes for the rest of us. Ton for ton, some of you probably have this math memorized, but generally speaking, a ton of cement produces about a ton of carbon dioxide. It's a very large amount of carbon dioxide for every ton of cement that's produced traditionally today. And there's energy input to effectively calcinize the limestone, which produces CO2 as the off gas. And so we've been building cement the same way for a very long time. And so the advantage that our solution has is that it doesn't require effectively significant energy input. It doesn't require or doesn't produce any byproducts like carbon dioxide. And it's an effective replacement out of the box for cement. So you start thinking about all the ways that we've been building cement for a very long time, we're able to bypass a lot of the hurdles and speed bumps that are in place today to allow us to get to a better solution. And as you start to think about how these threads get tied together, so you think about things like LEED and Built Green, these are really effective tools for people in the architecture trade or the building trade to understand the choices they're making with materials, whether it's bamboo or different other sorts of building materials, including concrete. You know, what are the choices they can make to reduce the carbon footprint of that particular project? On the other end of the spectrum are carbon registries, and there's these carbon markets that I'm sure a lot of you are familiar with that help to drive performance and behaviors and improvements as well.
And so we're very proud to be the first SCM material approved as a project participant under the Climate Action Reserve Protocol. So recently, CAR and a couple other registries have opened up these protocols for low carbon cement and low carbon concrete opportunities, and we were the first one to kind of make it through their process to be approved to earn carbon credits on the other side. And so we have the ability now to operate in this interesting space where we don't just have a solution that helps customers with checklists and points. We actually have an opportunity now to help industry by creating offsets that can be purchased for things that might be doing that are creating the need for those. So we're really excited about this as a future opportunity. There's a question earlier about, what is the relative strength of some of these solutions? We've done years of research through our friends at University of Washington to kind of put the science behind how zeolite composite concrete works. And so as you start to look at all the ASTM standards that are required for structural concrete in particular, and amazingly, pavers have to be almost twice as strong. The compressive strength after 7 days with a fairly modest amount of cement replacement is significantly higher. And the other tests in terms of look, feel, slump, and compression all meet or exceed the necessary specification. So in terms of the mechanical performance, the properties that you want and need from a alternative to OPC or limestone cement, we're able to prove this with evidence, and there's actually now peer-reviewed papers around this approach that show that our zeolite composite is an effective path forward. We have under the umbrella of zeolite composites different brands of businesses that we run. One that we created specifically for the consumer grade products that we have built in the form of these pavers, which is the one that's going around the room, is a business called Zeolock. And Zeolock now has a family of eco-green labeled solutions. These are water permeable pavers. Specifically, we chose this format because here in Washington, specifically King County, it's really hard to build anything these days that has an impervious surface, asphalt, concrete, or traditional pavers. And so what do you do, especially as there's higher density projects going forward, to eliminate those concerns or get around those requirements? And so water permeable pavers are a fantastic solution to that particular constraint for people that need to build a driveway, a walkway, a patio, other things that might be part of the architectural design of this project. These provide a significant outlet for not just the permeability requirements, but now if people are looking to reduce the carbon footprint, significant reduction in the overall project, they have a way to do that by just putting these around the edge of the structure. And this is one of the reasons that these builders we're talking to here in King County are so excited about this particular solution is that, number one, water permeable had been spec'd in. They didn't know this was an option because this is new. They're amazed that this is available commercially today. And they're really excited about getting all the extra points from these checklists because of the low carbon nature of the solution itself.
It's worth noting that the reason why this slide isn't right in here, it is literally available to be drop shipped to your job site tomorrow. And you're not sacrificing on any like concrete or concrete products, not sacrificing performance or durability. That can be emphasized. Everything we did was kind of backwards. In the lab, ASTM standards, including slump and pressure strength, water, like freeze-thaw, water absorption, all those tests exceed ASTM standards. And that's important to note because this is a solution that is available today, available yesterday.
We talked a lot about how solutions need to be cost effective. It's hard for people to make different choices and change behavior. Something's going to be a lot more expensive. So the zeolite itself is cheaper per ton than cement, and these pavers are the same or even a lower price than the equivalent. So we're really excited about bringing a cost-effective solution to the table that didn't exist before.
Sorry, just to confirm, sorry.
Yeah.
Is the SCM available tomorrow, or is it the pavers that are available?
Yesterday. Yeah.
Oh,
Yeah. Oh,
And then
yeah.
the Heidelberg one, to convert one of their silos, would be ready
Yeah. Yeah. And so I touched on this earlier, and I'm almost done. I think I have 9 pages. Okay, Jason, this will go quick. We talk a lot about a point of impact. And so what does it mean to have a lower carbon footprint solution? And usually people are talking about pulling carbon from the air, putting it into a wet cast product. We take a first principles approach. We think it's the best approach. It's sort of by design, sort of a lucky coincidence. But when we start to replace cement, we're actually preventing the CO2 from being created in the first place. Which, if you're preventing the CO2 from being created in the first place, it gives all these other solutions, carbon capture and other things, time to actually do the things that we need them to do. On top of that, though, we effectively have a carbon capture solution. So the paver that's being passed around is very quickly, over the first 28 days, absorbing CO2 from its local atmosphere, which creates a denser product. So that is going to be about half as porous as a traditional concrete paver. And it's going to have this, through this carbonation mechanism, it's going to have effectively a lower carbon footprint as it gets older than it did when it was born. And so there really are no solutions on the market that allow you to have kind of your cake and eat it too when it comes to avoiding carbon, sequestering carbon for a really good, effective.
Yeah.
Great.
I just gotta say, we gotta wrap it, 'cause I gotta do one more thing, and then we gotta
We're
do
done.
to it. Okay, I'll go.
Yeah.
Thank you.
You said yes. Yeah. Question.
The material that you're sourcing is like a mineral in the ground, right? Usually, is there not any concern about the habitat degradation that's caused by scaling up the production of this material or GWP reduction across the entire United States?
It's a good question. So our zeolite source is effectively the surface of part of the Mojave Desert. And so when we mine, and I use mine with air quotes, it's effectively excavation. So we're literally taking a giant shovel and scooping out the top 5 to 10 feet and putting it in a dump truck, sending it to our plant, processing it, and then you get this format of zeolite. And so the process by which we get the right to mine that area and continue to care for the area, there are restrictions in place to ensure that the habitat isn't degraded to a point where it's different from where we started. And so there's other mechanisms we have in place to backfill and other things if necessary. But we have a very minimally intrusive excavation process, which is also an advantage too, because limestone you're blasting out of the mountain. A lot of these other solutions, you have to do really unnatural things to even get to the source of the material in the first place. And so we don't have that same problem, which is another advantage we have. The GWP for the zeolite is actually something we're going to establish formally. We're going through an EPD process right now. And so in the next probably 2 months, we're going to have an EPD for the zeolite ingredient. So that can be an input to anybody's calculations and also the paper itself. And so we'll have very specific evidence on what that changes.
Great, thank you.
One other question about the paper, is the actual material permeable or is it just the spacing that allows it?
It's the space.
So we're working on also a pervious pavement product. So we are doing that in conjunction with the University of Washington Tacoma, and then all the concrete work's being done at the main campus. But we are developing a pervious pavement also.
Okay, before we move on to tour, we just have one last very brief speaker.
Yep.
Just for 2 minutes. Corey, if you could just tell us what Heidelberg's doing currently.
Sure, if you want to speak up here, you'll be on mic and camera. Sorry for the tripping hazards.
All right, my name's Corey, but you can guess where I work.
You already know.
Yeah, John invited me out here to say a few words tonight, so I just mainly wanted to introduce myself. I cover the residential market for the greater Seattle area. I've been working for Heidelberg about 2 years. Most of my professional career I spent in the military. Did a couple of years in snowboard sales and logistics, and somehow ended up in Contact. So, for better or for worse, you got the fresh guy. But on that note, I'm here to learn. This is my first time here, and I really like being around folks like you because you voluntarily are interested in this sort of a thing. Whereas I don't need to tell you, a lot of people in this market, in this industry, aren't interested in those they're told they have to. So that really piques my ears. You know, we do offer low carbon concrete, such as stuff that Dave spoke about, you know, where we recycle aggregates, we use SEMs, where we source close to home, you know, we use type 1L cement, and I'm happy to tell you all about that. But what I also want to do is hear what interests you and what you want to accomplish and how you can work with a local ready mix supplier to accomplish those things. So Sounds like there's a local watering hole meetup after this. I'll be there. So feel free to bend my ear. And then my colleague Durham is here to represent our cement side as well. So feel free to bend his ear as well. Thank you.
Okay, thank you very much. So next, Mike Raymond from the apprenticeship program is going to introduce our tour, and you can take us for a tour, and Rebecca's going to tell us about the watering hole before we run out there.
Before you go to the watering hole, just go ahead and walk through the building over here and do a little tour of our shop. So I did share a lot why we're a part of this, but the other thing too is I want to let you know that I talked about workability. So we've had some of these materials. I'll throw a little shout out. We threw up to 50% zeolite as a replacement for Portland cement in some of our patching, and it was very workable. And it did the task that we asked it to do for a patch repair job in the concrete. And it's those relationships that we're hoping to engage amongst all of us here, because you need to understand the workability and how it's going to perform out in the field once we start giving it to customers. So just a thought when you think of that here. And the other part, these are Lindsay's creations that we see. We went on a journey about a year and a half ago. We started a year and 4 months ago. We started our journey together, and it's an innovation on using material in a different way, right? In a more productive, efficient, less wasteful way. So we're excited for that, and we're excited for you all to come up with the ideas of how we can reduce the cement content and create structures and practice it with you. So we encourage that. If you have any questions and would like to practice your thought, your concept, we got a location right here that you can do that at.
And before we head out, a couple of things.